So given a white ellipse and a point on its border, this red dot here that I can place anywhere, okay, as we saw in the last video, there's going to be an associated maximal distance point on the border. And let's go ahead and draw that. So here's a maximal distance point with respect to this one, such that the sort of out of all possible points on the border of the ellipse, this one here is the furthest from the red dot. And when it is the furthest, the normal at this point is going to point or face the red dot directly. So of course, if I move my red dot around, my furthest out point is going to be moving around like so. Okay. Now there is a little instability or sudden jump that happens when something occurs, and I'm going to draw a so-called ellipse evolute, this asteroid. This is a well-known locus of the centers of curvature of the ellipse. Okay. Now you can see here that the line that connects this furthest out point towards point of choice is going to be tangent to the asteroid. Okay, and likewise, if I were to draw a line that followed the normal from the red dot, you'd also find a different tangency point to this asteroid that would probably happen just about here. But an interesting thing is the following. If this red dot is outside the asteroid, there's only one point on the entire ellipse boundary whose normal faces the red dot directly. Now, as I approach this little arc of an ellipse, this arc of the ellipse, which is internal to the asteroid, you'll see what happens. Let's go ahead and do that. So let's go toward the asteroid with the red dot. I'm moving the red dot. Now, as soon as I cross to the interior of the evolute, two other points pop up on the boundary of the ellipse, which also have normals that point toward red. So in fact, I have a cubic equation that is being solved behind the scenes. And this cubic equation may have three real roots, as it is the case now. So there are three real points on the boundary of the ellipse whose normals point toward red. Or if going back, if I'm outside of the evolute, this cubic has one real root and two complex ones that I cannot see right now. So there's always three solutions, but there might be three reals when I'm inside the asteroid, okay, or one real and two complex if I'm outside. Now, what's the relationship of this fact? So let's go ahead and follow with what we were talking about in the previous video, which was it was a sudden jump of the maximal distance point on the ellipse, which continues to be this one, from one side of the ellipse to the other side. Now let's continue to track what happens to these three solutions to the cubic, the 3 points on the boundary of the ellipse, that point toward the red dot, as I escape on the other side. So I'm going to escape on the other side. You can see that these two solutions here to the cubic are starting to join together. And then at some point, I jump out and I retain that single real solution over there. Now, you can tell that if I'm outside the asteroid, that single real solution is going to be the maximal distance from the red dot on the boundary of the ellipse. When I go into the asteroid, okay, it continues to be the maximal. This distance here continues to be the maximal distance. However, as my red dot approaches the middle portion or the bottom vertex of the ellipse right here, I get into the symmetric situation. It's a perfectly symmetric situation. I have three real roots, and these two real roots here are identical. What that means is that this distance and that distance are the same. So if I'm looking for the point on the ellipse boundary that is the farthest away from the bottom vertex, I actually have a tie between these two solutions here. Of course, this middle one here, by inspection, is going to be a shorter distance. It's just simply twice the minor axis of the ellipse. So I have a tie. But the crucial statement here is that as soon as the red dot crosses from one side of the, say, x-axis into the other side of the x-axis, so I go from a negative x to a positive x, I go over the bottom vertex, this tie is going to be broken. Let's go back to this situation here. I am sufficiently away on the left side of my bottom vertex. Which one of these two arrows here has the longest distance? By inspection, this is a longer diagonal than this diagonal here. Okay, now as I go to the center, the two diagonals are identical, and as soon as I cross over to the right, okay, I get the opposite situation. Now this diagonal here is going to be longer by inspection than this diagonal here. So if you were actually dynamically looking for the point on the ellipse boundary which is furthest away from the red dot, you would experience a discontinuous jump. Okay, I'll be tracking this point here as being the furthest away, and as soon as the red dot crosses the bottom area here, I would jump to that other solution of the cubic. So this is why we're getting this discontinuous jump. Of course, this jump is not being illustrated here. We're seeing just the roots of this cubic continuously, but you can imagine that if you're actually tracking the furthest away point, I'd right now be preferring this guy instead of that one there. But just a small motion to the left on the red dot would exchange my preferred furthest distance to this one over here instead of that one over there. Is that clear? Okay, now of course, as I exit the asteroid, the red dot is going to exit the asteroid, this point here, which is now my preferred cubic root, furthest away point, is going to remain the furthest away point as these two other roots join together and then become complex. So you can see here that they are almost together there, and now they're going to become complex, but it doesn't matter because from the perspective of the furthest away distance, these two guys are shorter than that one, so that one is going to remain the furthest away distance. And all the way around the ellipse until I hit the other side of the ellipse, right? So let's go back to this position here. You can see that I only have one real root until I hit the asteroid on the top there. And let's try to do this smoothly. So when I hit the asteroid and I go to the interior of the evolute up there, again, I'm going to have my 3 cubic roots, but it doesn't matter because these two roots here, which just got formed, are at a shorter distance from this root over here. So this one remains the champ until the red dot up there will pass through the top vertex, in which case I'm going to have this symmetric situation, and then discontinuously, this favorite or this furthest away point is going to be replaced by this other point over here as red moves to the left. So you can see there, now this is clearly a longer distance to red than this one is. Okay, so you get this phenomenon. And this explains that sudden jump. Now, let's now change the aspect ratio of the ellipse to something that gets closer to square root of 2. So right now, my aspect ratio is actually equal to the golden ratio, 1.1803. It's preset by this application. By the way, guys, if you want to check out this application, I left a GitHub address down here. Feel free to go there. And this is available online at this particular address up here. So let's now compress the aspect ratio of the ellipse to something that gets closer to, say, 1.5. It's at 1. Let's stop it at 1.5 right here. Okay, so here I'm at 1.5. I still have my asteroid. Okay, you can see that this asteroid still pierces to the boundary of the ellipse. So I'm going to get the same phenomenon as I move this red point in and out of the asteroid. I'm going to switch from 1 cubic root to 3 cubic roots. And these roots correspond to those points on the boundary of the ellipse whose normals point to the red dot. So you can see here that I'm going to cross into, the red dot is crossing into the asteroid. And these two brand new cubic roots that are real materialize, right? So they annihilate each other when I'm on the asteroid. In fact, they become a single root, and I get into this singular configuration where the cubic is only going to have 2 roots, 2 identical real ones, and a second distinct real one. But as soon as I cross out of the asteroid, those 2 identical real ones become complex and distinct and conjugate. Now, if I'm inside, I have these 3 real roots. My furthest out point is still this one. Pretty soon, this guy here is going to be preferred as I approach the center position. Now they are the same. And as soon as I cross the center position, this furthest out point is going to jump discontinuously to this point over here. Okay, so I've jumped now. So my favorite point is this one right now. and then as I exit the asteroid, I go back to the single root situation. Now, let's continue compressing the aspect ratio of my ellipse. It's at 1.5 right now. Let's see what happens as we approach square root of 2. This is a well-known result. So square root of 2 is approximately 1.412. Now, this is a well-known result. The evolute of the ellipse, the asteroid, the top and bottom tips of the asteroid are going to be touching the top and bottom vertex of a generic ellipse when a over b of the outer ellipse is equal to exactly square root of 2. And this can be easily verified. The equation of the evolute is closed form. I think it's a cubic. Actually, sorry, it's a quartic. Think about this. So how many intersections can I have here with a straight line? 1, 2. This could be a cubic, okay? Yeah, if we check out Math World, I think the asteroid is a cubic curve, parametric curve. But what happens at this situation here? Square root of 2a over b. The asteroid is just touching the top and bottom vertex. So what's going to happen is I'm not going to have the situation when the red dot is technically inside the asteroid, okay? When my a over b is bigger, okay, I can be inside of the asteroid and have 3 roots. But if a over b is square root of 2 or below square root of 2, I can no longer do that. So as I compress the ellipse, my asteroid is also shrinking until its top and bottom tip touch the ellipse right there. And I'm pretty close to square root of 2, and exactly at square root of 2, I have this perfect 1-point intersection of the top and bottom tip. So now if I move my red dot, I can no longer be in the interior of the asteroid. So there's not going to be a discontinuity because I can never have a situation with 3 roots and a symmetric situation and then switch discontinuously from one solution to the other. So if I shrink the asteroid or the a over b of my ellipse further down below square root of 2, now my asteroid is completely interior to the ellipse. And of course now I'm always only going to have, no matter where the red dot is, I'm only going to have a single solution to my cubic, a single real solution, and I'm just going to have this very smooth transition. Very smooth transition. So this is what we experienced in the previous video.